Hey everybody, it's Ripley back again. We're going to talk about a really cool algorithm called Newton's method. And this thing, the best part about Newton's method is that some variation or another of it is still present in graphing calculators today. Like it's basically a computerized mode of thinking, which is just amazing. So what I want to do is I'm going to show you how to use Newton's method to solve for something like, let's do the cube root of 11, okay? Now, the cube root of 11, easy for us, right? All we do is we grab our little calculator and we put in, let's see, 11 raised to the 1/3. And we know it's going to be about 2, right? It's going to be, because cube root of 8 is 2, and cube root of 27 is 3, so it's going to be 2 point something. But being able to do that, having our calculator do that, is amazing if you really think about it, because back in the day, they had to do this by hand. And it was awful before Newton's method. There were other methods that they used, but it was awful, all right? So what I'm going to do is I'm going to show you the thinking behind Newton's method. The most important thing that you understand to get started is that if I want to figure out the cube root of 11, then really what I'm doing is I'm solving for the roots of the function x cubed minus 11 equals 0. Right? So think of this function that I just drew here, I drew it in advance, as f of x equals x cubed minus 11. All right. Now follow my thinking here just a little bit. Let's grab this guy. What Newton's method says is, let's pick a guess, something that we're just guessing. So we know it's around 2. So I'm gonna say that this is x equals 2, and this is going to be our guess. And then what Newton said is, let's go down to the curve, and we're going to build a line tangent. Ooh, that's a pretty good one. Now, if this is our guess, if our guess is what we call x naught, so I'll let x naught equal 2. All right, this is 2, which is our guess. Now what we do with this is x naught is 2, so this becomes x sub 1. Now I'm going to change colors again. What does x sub 1 do? X sub 1 goes back up to the curve and draws another tangent line. Now look what's happening. This new tangent line gives me a new x-intercept. So all I'm doing is grabbing my x-intercepts. This is going to be x sub 2. Now what happens? I'll only do this one more time. I go up to the curve. I draw another line tangent. Now, if I were to zoom in on that, what would that look like? Well, I'd have that same, I'd have this guy. Here's my curve. And what it's doing is it's getting closer and closer to the x-intercept. Isn't it? It's zeroing in on it. So here's the way it works. Look. You guess. You go down to your curve. You build a tangent line. You find the new x-intercept of the tangent line. Remember, the tangent line is just an approximation for the curve anyway. That new value of x becomes your new quote-unquote guess. That goes back up to the curve. You draw a new tangent line using that new point. That becomes x sub 2. That's your second guess. That goes up. Then we find it, right? We get closer and closer and closer. That's what's so cool about Newton's method is not only is it an effective way, not only is it an excuse me, that was my email going off, an effective way to come up with approximations for zeros, or in this case, for the cube root of 11, but it does it really fast. But let's build it for a sec, shall we? Let's make sure that we build this thing. So let's think about the process. What do I have? This point right here is x naught, f of x naught. True? The slope of that line is f primed of x naught. And what do? We just build a line, all right? And that line, we're then going to try and figure out where that line intersects the x-axis. So let's look. I know that y minus f of x naught is equal to f primed of x naught, that's my slope, times x minus x naught. You with me? All right, that's the equation of my line. Now, think about this for a sec. just for a sec. What I'm trying to do is I'm trying to figure out when this line crosses the x-axis. That's what I'm trying to do. How do I figure out when something crosses the x-axis? Well, I set the y equal to 0. If I set y equal to 0, that will tell me when this line crosses the x-axis. But what I'll end up with is, if this y goes away, and now here's what I'm trying to do. I'm trying to solve, let's change the color here so we can really see. I'm trying to solve for that x value, which becomes our new guess, right? This is the value of x that becomes our new guess. So in a puff of algebra, this guy's going to go away to 0. I'm going to end up with, let's go back to black, negative f of x naught divided by f prime of x naught is equal to x minus x naught. So in a quick little puff of algebra, this becomes x is equal to x naught minus f of x naught over f prime of x naught. All we did was use the equation of a line tangent. Well, all we did was use an equation of a line, which has arguably been around for thousands of years. Now remember, this x-intercept of this first line tangent becomes our new guess, and then we just start the process over again. So what Newton's method did is it came up with an iterative process, an iterative algorithmic process, by which I can always find x sub n plus 1 by having, as long as I know the value before, prior, I would have x sub n minus f of x sub n divided by f prime of x sub n. It's so cool. It's ridiculous. And watch how fast it works. Now there's going to be some irony here. We're going to use a calculator to solve for the value that we needed a calculator to solve for in the first place. But while that's notable, it's not important because for two reasons. Firstly, the people back in this day and age were really good at calculation. They were much better at calculation than we were because they had to be. All right. Well, the other part is it's what I want you to see is the algorithmic process. And think about how easy this would be able to be to be able to write this in a code. Super easy. Why do you think when you use your calculator to solve for zeros, why do you think it asks you for a guess? Guess why? Because Newton's method. That's why. Now, there are probably algorithms that are faster, maybe a little more slick, maybe a little more efficient, or quick in terms of the way in which they process it, but I would bet if you cracked into that code, it would have remnants, at least, if not the outright algorithm that Newton put forth for us. Okay, so let's do this thing. We're gonna let our guess be 2. We know that f of x is equal to x cubed minus 11, right? That's our function that we're solving for roots for. Remember, the whole goal of this is to figure out what the cube root of 11 is. I know that f prime of x is equal to 3x squared. Okay? So I'm just going to follow the algorithm. X sub 1 is going to be our guess, which is 2, minus f of 2 divided by f prime of 2, which is equal to 2 minus f of 2. This is going to be negative 3 on top, divided by, what is that, for 12, right? If I want to clean this up even just a little bit more since I'm doing it by hand, this is going to be 2 plus 1/4, which is 9/4. Okay? X sub 2, whoa. What do we know that this is? This is 2.25, right? X sub 2 is going to be 9/4, I'm just following the algorithm, minus f of 9/4. Now this is where it gets a little bit ugly. All right, f of 9/4 divided by f prime of 9/4. Now, I don't want to do this by hand because it's awful, right? But we're going to get a number at the end. So what I'm going to do is I'm going to show you how to use your calculator to sort of go through the algorithmic process. And I'm going to be a little bit lazy, okay? I'm going to be a little bit lazy. You could easily program a calculator to do this, but for those of you that aren't fantastic at programming, this is not a programming class. This is a calculus class, and right now we're studying Newton's method. But I'm going to show you how to sort of let your calculator run the algorithm for you. okay, other than actually having it put in the cube root of 11. I know it's kind of crazy that way. Okay, you ready? All right. First thing that you want to do is put your guess in. So you put 2 in and you hit enter. And then all that I'm going to do is I'm going to hit second answer minus, now you remember that our function was x cubed minus 11, right? So I'm going to do parentheses and I'm going to go second answer cubed, got to scooch over, minus 11, end paren divided by, remember the derivative was 3x squared, so this is going to be paren 3 second answer squared. Now I have to use, let's go over this really quickly. I got to use these parentheses because otherwise what my calculator will do is it will only divide through by the 3 first and then multiply by the answer squared. And if we look back on this, remember what I need is, I need that 3x squared down here, okay? You with me? Now, recall, I'm going to toggle back and forth between these guys. This code that I just wrote, or excuse me, I guess this would be a command that I wrote, what it's basically doing is it's taking this answer and it's plugging it in, right? My answer being 2. I just hit 2, which is my guess, hit enter, and that becomes the answer that gets stuffed into this equation. Watch. When I hit this, I get 2.25. When I hit this again, I get 2.24. Let's put that in here. 2.224. Let's go 427. 2.22427. So I know that x2 is 2.22427. Now here's something that's really cool. Notice that these two digits are the same. That means they're locked in. You are locked in at 2.2. So if you just had to get close to the cube root of 11, you could say, it's about 2.2 after 2 iterations, and you're done, okay? All right, let's go back to this, though. This is fun. Now, here's the best part. Is your calculator, if I hit this again, watch what happens. It redoes the last code that I did, and it uses 2.224279835 as my answer that it stuffs into the command. Watch. Pow! 2.22398. Let's write that up. All right, where am I? Okay, x sub 3 is going to be 2.22398. Guess what? I just locked out because this is 2.2, this is 2.224, this is 2.223. Now I'm locked out to 2.22. Let's do it 2 more times and see what happens. Hit enter. 2.223980. Oh my goodness, look at what's already happening. I've got 2.223980 is now officially locked in. Let's do it one more time, and I'll bet you we're there. Look at that, the whole thing. And I would be remiss if I did not put what the cube root of 11 is, and we'll put it right alongside since we can't see it. Pow, look at that. Amazing. It's amazing how quickly it works, how efficiently it works, and how accurately it works. So by, what did we say? By x4, I had 2.22398. Was it 001? Can I read it? 3980091. 3980091. Which is as close to the cube root of 11 as your calculator will get for you. All right, go away. All right, that's it. Ladies and gentlemen, we have Newton's method. Not very difficult. I think it's super fun and super cool. Pretty useful. Enjoy, and I'll see you in the next lesson.